everyone, in this video we will introduce the normal model, one of the most common continuous distributions in statistics and one of the backbones to statistical inference or statistical decision making. So let's go ahead and jump in. We will first talk about properties of the normal model, what it looks like, when we might use it. We'll also introduce how to find percentiles, quantiles, or probabilities from a normal model. And then finally in this video, we'll talk about how we can tell whether or not a variable follows a normal model. So let's start with an application that we can use. So forced expiratory volume, or FEV, is an indicator of successful lung function. What this corresponds to is the amount or the volume of air that a person can blow out of their lungs in the first second after fully breathing in. A study was done on a sample of 654 children. Variables that were measured in this study include the children's age, their FEV, their height, sex, and whether or not they had been exposed to secondhand smoke. What we'd like to do is come up with a model that might be suitable for forced expiratory volume. So first, let's just see what this variable looks like. So here you're seeing a histogram of forced expiratory volume. The code that generated this histogram is on the left. What can we see when we look at this histogram? Well, it's unimodal. There's one clear peak in the data right about here. Most children, it looks like, have a forced expiratory volume somewhere between a little bit less than 2 liters and around 3 liters. There does appear to be perhaps some skew, but for the most part, this is a fairly symmetric distribution. Let's take a look at another variable in this data set. This is the distribution of height for the children in the study. We see the same sort of unimodal pattern here. This distribution is also quite symmetric. Now, it turns out that this shape that we have, that is sometimes referred to as a bell-shaped curve, so something that is unimodal and fairly symmetric, is really common in nature and in the medical sciences. So much so that we in fact refer to a distribution that looks like this with the normal model, or the normal distribution. So the normal model is actually a continuous probability distribution. What that means is that any value within a particular range is allowed for this distribution that describes a symmetric bell-shaped curve. Now, this normal model has two what we call parameters, so two values that help us define this normal model. They're the mean and standard deviation. We'll denote the mean of a population model with a lowercase Greek letter mu, so that's right here, and then the standard deviation of a population model with a lowercase Greek letter sigma. So these two numbers will help us characterize the normal. The normal model is sometimes called the normal distribution. You may have also heard this referred to as the Gaussian model. This is a fantastic approximation for many variables that we see out in nature. So let's talk about some properties of the normal model. Here you have a plot of what this normal model looks like when you graph the formula. And there's a couple properties of this model that I want to zero in on. This is a continuous distribution. The way that we measure probability with a continuous distribution is a little bit different. We look at area under the curve to help us define this. So for example, if we wanted the probability that x is between, say, 0 and 1, what we would need to do is actually find the area under this curve between 0 and 1. The normal distribution is symmetric and unimodal. So the highest point of this distribution is the mean mu. Here in this plot, the mean mu happens to be 0 because that's the highest point. Now, to find the probability of observing a range of outcomes, so for example, observing a value of x in this plot between -2 and 0, we do need a way to find the area under the curve. Now, if you've taken calculus before, you are probably beginning to grimace just a little bit. At the end of a Calc 1 class, for example, you would have learned how to find area under a curve using integration. That is harder with the normal model. It's harder with the normal model because of the form of the normal model. So this nice simple looking curve is generated by this function. The normal probability density function, as we refer to it, is 1 over the square root of 2 pi sigma squared times e raised to the negative x minus mu quantity squared divided by 2 sigma squared. So this is kind of a handful. In general, we don't want to integrate functions that look like this. That means that finding area under the curve is going to have to be done a slightly different way. Now, traditionally in a statistics class, what we would have done is look at a table of probabilities under the normal curve and used that table to help us solve a given problem. However, in my practice as a statistician, I don't use tables. I think that most professional statisticians avoid using the tables at all costs. So we'll look at some functions that we can use in R to help us out. Now, there are two functions that we'll typically use. In base R, so R without any extra libraries, the p-norm function calculates probabilities under a normal curve. The q-norm function calculates what are called quantiles or percentiles. So what probability has occurred up to a particular point. Now, we like to use those additional libraries in R because they make life a little bit easier. The ones that I like to use a lot when I'm working with normal variables are called xp-norm and xq-norm. These come to us from the Mosaic library. That x means that there's a little something extra to these functions, and let's see what the extra is. So we're going to apply the normal model to the lung volume of children in the FEV study. When we looked at this histogram, it was a little bit skewed to the right. However, we did have a unimodal, decently symmetric curve, so this model might be a good approximation. In order to apply this approximation, I'll assume that my sample mean of 2.64 is a close approximation to the population mean, so I will set mu equal to this. I'll also make the assumption that the sample standard deviation is a good enough approximation to the population standard deviation. So that's where I'll get my values or my parameters for this normal model. Okay, so let's assume again that forced expiratory volume follows a normal model. We're assuming that the mean is 2.64 and that the standard deviation is 0.87. We'd like to find the probability that a child has FEV or forced expiratory volume less than 1.5 liters. In order to do this, we'll use the p-norm function in R because we want to find probability up to a particular point. 1.5 is the value of interest that we care about, so that's the first option. We then introduce the mean equal 2.4, standard deviation equal 0.87. The result that we get here is 0.095. So what that tells me is that 9.5% of children have a forced expiratory volume of 1.5 or fewer. So that's the base function. Let's take a look at that XP norm output that we get using the Mosaic library. So the XP norm output is a little bit more informative. The XP norm inputs look exactly the same. The only thing that has changed here is that we've added an x to this function. Not only are we given the probability up to a point, we're also given a plot of what this normal model might look like, and the area up to the point is shaded in purple. So this tells us quite a bit. Now, if you try this code at home in RStudio, you're going to see even more output be presented to you in the console. So this is incredibly powerful in terms of the amount of information that is coming, and let's be honest, who doesn't enjoy a good plot? I love a good data visualization, so I like this function a little better. Now let's talk about finding quantiles. So again, we're assuming that FEV follows the same normal model. I want to know what the lung capacity is for the lowest 40% of children. So what's the lower limit of lung capacity up to 40%? So here, because we want to find a quantile, or we want to look at the cutoff for the lowest X%, we will use the Q-norm function. So Q-norm gets 0.4, mean and standard deviation are still the same. We get an answer of 2.4. So what this tells me is that 40% of children have a lung capacity of 2.4 liters or less. Now again, contrast that with the XQ norm output. We get the same value returned, but we also get a nice plot of what this normal model actually does look like. So let's take a look at another application or another example. So suppose that the baby's born in single births, so no twins, no triplets, just one at a time, have birth weights that are approximately normally distributed, with mean 3.296 kilograms, standard deviation 0.560 kilograms. Now, here's what we'd like to do. We'd like to find the probability of a baby being born weighing between 3 and 4 kilograms. We'd also like to find the probability of a baby being born weighing more than 5 kilograms. Take a moment on your own to think about how you might use these functions to help you answer this question. Okay, so we're going to have to be a little bit creative in how we approach this problem. Let's zero in on that first question. What's the probability of a baby being born weighing between 3 and 4 kilograms? Well, we know how to get the probability that a baby is born weighing less than 4 kilograms. We'll use XP norm, our mean and standard deviation, as given. So 89.56% of babies are 4 kilograms or less when they're born. We also know how to get the probability less than 3. So 29.86% of babies weigh less than 3 kilograms when they're born. So then to find the probability that a baby weighs something between 3 and 4, here's what we'll do. We'll take that bigger probability, the probability that the birth weight is less than 4, subtract away the part that we don't want, which is the probability that the birth weight is less than 3. So plugging that in here, I've just gone ahead and used R directly as a calculator. We take the previous probability, 0.8956 minus 0.2986, and we get that about 59.6% of babies who are born are somewhere in this 3 to 4 kilogram range. Now, if we want to find the probability that a baby is born weighing more than 5 kilograms, we'll have to think back to our probability rules, namely the complement rule. So we can use this XP norm function to help us find the probability that a baby is born weighing less than 5 kilograms. So 99.88% of all infants are less than 5 kilograms at birth. In order to find the probability of weighing more than 5 kilograms, we would just take the complement or 1 minus this. We'll get a very small probability, something like 0.12% of all infants are more than 5 kilograms. Now, in order to compare different values against normal distributions, we might need to use a little bit of algebra. Look back on this plot that's created with the XP norm. We get a value added here that we haven't really talked about yet, something called a z-score. What is this thing? Well, this z-score is a standardized normal value. So essentially, in order to calculate this z-score, what we're doing is taking the observed value x, we subtract the mean from the normal distribution mu, and then we divide by the standard deviation sigma. What this z-score tells us is something very special. This tells us how many standard deviations an observation is from the mean. If we have a negative z-score, that tells me that we have an observation that is below the mean. Then if we have a positive z-score, that indicates a value that is above the mean. So think of this z-score as a unit of distance. How many standard deviations away are we? It turns out that z-scores themselves are also normally distributed, and they follow a special normal distribution called the standard normal distribution. The standard normal distribution is actually one that you've seen before when we first introduced the normal. The standard normal has mean 0, standard deviation 1. So it looks like this. From that standard normal, we can come up with a pretty nice rule of thumb for working with normal distributions. So let's say that we don't have R or a normal calculator with us, and we want to find some quick ranges for where we think values might fall in a normal model. One tool that we can use to help us here is the empirical rule, and here's what that says. The empirical rule gives 3 bounds or 3 ranges for values from a normal distribution. So about 67% of all the probability in a normal model is contained within this range, contained within the mean mu minus a standard deviation sigma, and then mu plus sigma. So if we take mu plus or minus 1 standard deviation, we'll capture about 68% of the probability. If we go a little bit further, add and subtract 2 standard deviations, we've captured about 95% of the probability in a normal model. And then going out even further to 3 standard deviations, we've now contained nearly all, about 99.7% of the probability in a normal model. Visually, here's what the empirical rule, actually looks like. So most of the probability, about 2/3, 68%, is within 1 standard deviation of the mean. Go out a little further, we've now reached 95% of the probability. Go out a little further, 3 standard deviations covers just about all of it, about 99.7% of the probability. So let's apply this to birth weights. So the babies born in single births have birth weights, again, distributed with a mean of 3.296 kilograms, standard deviation 0.56 kilograms. We'd like to find a range for the middle 68% of all birth weights, middle 95% of all birth weights, and then again, all birth weights. In order to do this, we will add and subtract values from the normal model. So in order to get that 68%, by the empirical rule, we'll add and subtract 1 standard deviation. 2 standard deviations will give us the 95%. 3 standard deviations will give us nearly all. And we'll get a lot of practice doing these calculations in class. Now, this empirical rule is limited. It only works for data that is approximately normal. So if your variable is roughly symmetric, roughly bell-shaped, unimodal, you can apply this empirical rule to find some quick ranges. However, if our data is not normal, we should not be using the empirical rule. Okay, so the last thing I want to talk about in this video is how we can actually work with this normal model. So how do we know that our data fits a normal model? One tool in our arsenal that we can use is something called a QQ plot. So what a QQ plot stands for is quantile, quantile. And what it does is plot the sample values from our data against the corresponding theoretical quantiles from a normal distribution. So for each observation, we calculate a z-score and then plot our observed values against where that z-score would fall in a normal model. Now, if our variable looks approximately normal, if it follows a normal model, this QQ plot should look like a straight line. In order to get a feel for what these things look like in practice, I've simulated some data. So let's look at a few QQ plots. Here are 3 examples of various histograms that were generated using a normal model. So these all, in theory, came from a normal 0-1 model because I generated the data myself. We have a small data set here on the left with only 30 observations, a reasonably medium data set here with 100, and then a large data set with 300 observations. Notice that the more observations we have, the closer this histogram gets to that classic sort of bell-shaped curve. Now here's what the QQ plots look like. You can tell that they fall roughly along that straight line, but they're not perfect. There are some points, for example, that are a little bit off from the line. Most of them do fall sort of on a straight line. In a QQ plot, these are what you want to see in order to support your data being normal. Small deviations, especially on the end, not too bad. Now let's contrast this with what it looks like when the data is really not normal. So here are some clearly non-normal data sets. Again, I know these are not normally distributed because I generated them myself using other distributions. We have on the left a distribution that is very clearly bimodal. We then have a skewed left distribution and a skewed right distribution. So how do these QQ plots look? These QQ plots are more problematic, especially with the bimodal QQ plot on the very left. You see a strong S shape in the curve. This is a clear indication that your data is not normally distributed. The skewed left and skewed right data sets are a little bit closer to that straight line, but you also see a curve in them, either concave down in the case of a skewed right or skewed left, and then concave up in the case of a skewed right distribution. So if you see that curve or an even stronger S curve in your QQ plot, right away that should be an indication that the data is probably not normally distributed. We're looking at this from a bird's eye view, so think about what this would look like if you stood at the other side of the room and looked at the plot. We're looking for obvious deviations here. Okay, so let's go back to this forced expiratory volume situation. Is the normal model going to be reasonable? Well, we can look at a QQ plot. Here's how we can create one of those in R. So we'll use ggplot to create the initial plot. We'll use a plus sign to add some layers to that. So the first thing I'll do is add a stat underscore QQ. That's what plots the points itself. I'll add stat underscore QQ underscore line to create that line to compare things to, and then I've added a label here indicating that this is a QQ plot of height. We can see that most of the heights do fall along that point. There may be some slight curvature in this QQ plot. So height could be modeled using a normal distribution, but there might be some hesitations here. Looking at gender, does gender make a difference in height? Absolutely. The curve becomes more pronounced. So maybe once we have accounted for gender, height isn't that normally distributed after all. In the next video, we'll start talking about how we can use the normal model to think about variation in data, specifically variation in repeated samples. I'll see you then.